Students, I welcome you to in this another video tutorial in the series of computer system architecture. And in this lecture I am going to explain you the each and every step of full adder. So what is a full adder? Full adder is used to adding 3 bits. It adds 3 bits and it takes 3 bits as an input, and in the output there are 2 variables that it gives, which is sum and carry. So sum and carry is generated when we add 2 bits or 3 bits, as we have seen in the half adder. So the 3 bits, so what are the 3 bits and what are the various combinations from these 3 bits? So as you know, we have 3 bits, so we will have 2 raised to power 3, which is 8. So we will have the 8 combinations like 0 0 0, 0 0 1, right, and 0 1 0. 0 1 0 is in the decimal, we know that it is 2, right? And then for 3 we have 0 1 1, so 0 1 1, and 1 0 0. Then we have 1 0 1, then we have 1 1 0, right? 1 1 0 is your 6, right, in decimal, 1 1 0, and then we have 1 1 1. So these all are the 8 combinations that are using 3 bits. We generate these 8 combinations from the 3 bits, right? So now, how the full adder adds these 3 bits? So in the output, as I told you in my previous video, that a carry is generated, okay, along with the sum, and a sum is generated. So I am using the symbol S for sum and C for carry. So let's take this combination of bits, 0 0 and 0. So in that case the sum will be 0, okay, and the carry, so there will not be any carry generated from this these combinations, right? But when we add 0 0 and 1, it gives sum as 1. Again the carry will not be generated, it will be 0 again. And in this, for this combination we have 0 1 0, so we add 0 to 1 first and then 1 to 0. So the sum will be 1 again in this case, and carry will be 0, right? Again here in this case, when we have 0 1 1, right? So in that case 0 1 will be 1 and 1 1 will be 1 0, because you know, and if you don't know about that how 1 1 is 1 0, it's very simple, because if you convert it into the decimal, it will be 2, and the 2 will be represented in binary. If we convert 2 into binary, it will be 1 0. So the sum will be 0, but the carry will be 1, okay. And in that case 1 0 0, we have sum 1 and the carry will be 0. Again in that case 1 0 1, it will be like 1 0 1, 1 plus 0 is 1, and 1 1 is 1 0, again 2, right? So the sum will be 0 and the carry will be 1. And like in this case, again we have the sum 0 and the carry will be 1, right? And in that case 1 1 is 1 0, right? Okay, so let's do it here, right? 1 plus 1, which is 1 0, right? 1 0, and when we add 1 again, this one, right, so it will be like, so let's plus it, right. Okay, so then 0 and 1 will be 1 and 1 will be 1 here, right? So the sum will be 1 and the carry will be 1. So in that case here we will write 1 carry and 1 sum, right? Okay, so so in that way we can easily generate the truth table for the full adder, and it's quite easy. So just what you have to do, for you need to just focus on the concept for the adding, and if the concept of half adder is clear to you, then the full adder will be very easy for you to generate the truth table of full adder, right? Okay, now so what is the next step to do? Next step, because this is the truth table, right? This is the truth table, and what we are going to do, as we have done in half adder, that this is TT I am writing is like truth table, right? So here, so what will be the next step? Next step is to generate a Boolean function for the C and S. Okay, so for that what we have to do, we have to draw a karnaugh map for carry and for sum. Okay, so for carry I am going to generate this, right, first. So as you know from the karnaugh map concept, that when we draw a karnaugh map, it is like this, right? It is a box, and which has some cells, okay, which is divided into cells, right? The cells are, so how or how many cells will be there in this K map for the C, for carry will be, so how to calculate the cells? So to calculate the cell, we have again this formula 2 raised to power n, where n is the number of bits, number of input bits. So here we have 3 bits x, y, z, so the n will be 3. So 2 raised to power 3 will be 8. So we will have the 8 cells in this karnaugh map, right? So let's divide it into 8 cells. So this is 2, this is 4, and this is 8 cells, right? So okay, now how to place the these 0 or 1s in this karnaugh map? So again I am remind you that we are going to generate the sum of product form. Okay, so we will consider only 1, so we will place 1 here in these cells, right? So take x on the left hand side of this, because there are 2 possibilities for x, 0 and 1, and for y, z we have the 4 possibilities, which is the combination of 0, 0, right, 0, 0, 0, 1, and 1, 0 here, and then we have 1, 1 here, right? And again, if you don't know, and if you are not aware, or if you have not attended my lecture and about the K-map in 3 variables, you can watch the videos in this series, right? So okay, now we have to place 1, okay, in these cells. So how to place ones? Again we have to place ones like 4, because the 1 is here and the 3 ones are here, right, in this position, right? So for this combination, when x is 0 and y, z is 1, 1, right? When x is 0 and y is 1 and z is 1, so we will place 1, okay? So when x is 0 and y and z as 1 1. So in this cell we have to write 1. Okay, then here we have 1. So 1 0 1, when x is 1, y is 0 and z is 1, right? So x is 1. So in this second row, right, if I consider this is the first row and this is the second row, so for x is 1, y is 0 and z is 1. So y is 0 and z is 1 in this cell, right? So we will write 1 here. Again likewise here we have x1, y1 and z0. So x1, y1 and z0, right? y1 z0 here, we will place 1 here. Okay, so we will place 1 here. Now again for this we have x1, y1 and z1. So x1, y1 and z1. So we will place 1 here. Now what we have to do, we have to make group. So if there is any group and if there is any possibilities to make a group, so we can easily make a group, and the group will be of the maximum number of cells. So we can make a group in multiples of 2. So first of all we will look for the group for the maximum number of cells. So maximum number of cells is 8. So can we make a group of 8 cells here? No, because we have only 4 ones here in these positions. Then we have to find the, can we make a group of 4 ones? No, it's not possible, because these 3 cells are adjacent together, but here we don't have the 1, or here we don't have the 1, or here we then don't have the 1. So we cannot make a group of 4, and it's not possible in that case. So then can we make a group of 2 ones together, or 2 cells together? So yes, it's possible, we can make a group of 2, and these are the groups that we can form. The first group is this, right? So for this group we will write the Boolean functions for C. So for C I'm going to write this directly, right? So we have yz. So for yz we have a 1 group. So because this is 1 1, so 1 1 is yz. So we will write yz, right? Then we can see from this karnaugh that we can make a group of these 2 ones together. So this is another group. So here we have now, what is the common from these 2 cells here? It is 1, it is 1. So we have yz and yz complement. So for yz and yz complement, and you know from the Boolean laws, and if you don't know about the Boolean laws, I just remind you that if this is the case, that which is 0 plus 1, it's evaluate to 1, right? 0 plus 1 is 1. Or in other terms, if I take a variable, any variable, let's say x, and I add this to its complement, right, like x complement, then it's always be 1, because plus represents the OR gate, and in the OR truth table we can see that if any of the input is 1, it evaluates to 1. So whether it's 0 plus 1 or 1 plus 0, it will be 1, and if both the inputs are 1, then it will be 1, right? So if you don't have any idea, or if you have forgotten about the OR gate, so you can refer to that video of logic gates. Here I have already explained about all the basic logic gates, from AND, OR, NOT, XOR, XNOR, and NAND, NOR. all the gates, right? So here because in this equation we can see that we can take a one common here for these two cells. So 1 plus 0 will be 1. So again we will left out with this one. On this 1 is represented because the first digit will represent the y and second digit represent the z. So in that case we will have the y from here, right? We will have the y from here and x from this side because it represents the x. So we will write yz plus x because we are considering only one in this K map, so we will write the sum of product form. Okay, and then we are left out with this. So this one can be merged with this one, so we can make another group. Okay, yeah, so 1 1. Okay, so in that case again using this formula we can see that 0 1 and 1 1. So we have this one common. This 1 is represent z and 0 plus 1 will be 1, so it will come out to be 1. So in that case it will be z, right? So and from this side we can see directly that this is x, right? So we will write plus xz. So here the one question that can comes in our mind that we have taken this one 3 times with this one and with this one, with this one and with this. So we can use this or any 1 or 0 in product of form any number of times. So don't worry about that. We have already made this first group and again we are considering this one with this because we can make a group of cells which are adjacent to each other. So no matter how many times you are taking it, okay, so we can take it as many times as we want if there is a possibility of group in that case, right? Okay, now we have come out with this Boolean function for C, which is yz plus xy plus xz. Okay, and for sum we can also repeat this. Okay, so just do it. Just draw a karnaugh map which will have the 8 cells. Okay, so let's divide it into the 8 cells. So 1 2 3 4, right? Okay, now draw a line here from this point and then again write x and yz, x here and yz here. Then we can see from here, right? Because 0 is here, x is means 0 means x complement, 1 means x, and then again for 0 0 0 1 1 0 and 1 1, right? So 1 0 will be here and 1 1 will be here. So now again look for these ones only, this one and this one. So we can look here that when x is 0, y is 0 and z is 1, so we will place 1. Okay, so in that case 0 0 1 will be 1 here, and for this we have x 0, y 1 and z 0. So y 1 and z 0 again in this right. Then we have this one. Here we have x1 and yz is 0. So x1 and yz are 0. In this cell we will place 1. And for this one we will have when x, y and z, all the 3 variables are 1. So here in this cell we will place 1, right? Now you can see there is no possibility of making a group because these cells are scattered in a way that they are not adjacent to each other, so we cannot form a group. Okay, so in that case what we have to do, we have to just write it as it is, right? So okay, so we have this as, let's take it more bright so it can be visualized more clearly. So again here, so for this we have x0, so we will write x complement, y complement and z, right? Then because it is a sum of product, because we are considering ones only, one only, so we have this one. So for this x complement, y z complement, because x is 0 and z is 0 and y is 1, so x complement, right? And then we have y and z complement. Okay, now again for this one we have x1 and y and z are 0, so we will write x and y complement and z complement. Okay, and then we will plus, because we have left out with this min term, okay, because these are the min terms. So here we have all the variables are 1, so we will write x, y and z. Okay, so here we can see from these two min terms, like this one and this one, so we can take a common of x complement. Okay, so we will take a common of x complement. X complement is this, right? And we have y complement and z, right, plus y z complement. This is y and this is z complement, right? And for this one we can take a common x, right? So we will take common x, and then we have this y complement z complement plus yz. Okay, now if you closely look to this Boolean function, this is nothing but your XOR gate, because these are added together by taking complement of one term at a time. So this is your XOR gate, right? And if you have no idea about the XOR gate, so I tell you, when both the inputs are different, it evaluates to 1, right? So you can refer again for the logic gates, and you will find here this type of equation in that XOR table, right? So I will write x complement and y XOR z, y XOR z. This is the symbol of XOR gate, right? So this is your XOR gate. And for this one, this is your x, and this function represents your NOR gate, right? So for the NOR we have two symbols. We can write y and then cross symbol, right? cross symbol. This is your NOR gate, and this JOR gate and NOR gate are opposite to each other, because in JOR gate, when both inputs are different, it evaluates to 1, and for the NOR gate we have like if both the inputs are same, it evaluates to 1. So they are opposite to each other. So what we can do, we can write is like that: y plus z complement, right? So what we can how we can write this? We can write this as plus. Okay, we can write this as plus. So plus symbol with its complement, right? With its complement. So now you can easily observe that here we have x complement, here we have x, here we have y or z, and we have complement of y or z. This is again same as this one. So we can write it as x XOR y XOR z. So it's come out with your Boolean functions for sum. So for sum we have x XOR y XOR z, and for C we have this yz xy plus xz. So you can now easily draw a logic circuit for this these Boolean functions for sum and carry, right? So let's take x, y and z. Okay, now we have this x, y and z, right? So here we have x, we have y, we have z. Because in exam they are going to ask you to draw a logic circuit for the full adder. So for full adder we have, if I take for this C, so we can see here that for y and z is your nothing but your AND gate, because it's the dot operator between these two. So we will have the like y and z. This is your AND gate, right? Then xy, for xy we have this they are combined with this AND gate. And again for xz, so let's take x from here and z from here. So we have this AND gate, and these all three are connected to plus, right? So plus operation is nothing but your OR gate, right? So this is your, they will be fed into this OR gate, and then we will evaluate with C, right? So let's take OR gate. Okay, and this is your logic circuit for C, right? Means for carry, right? And for S we have nothing but a XOR gate, right? So this is your XOR gate, and is very simple, right? So we have s here. Now for x and y and z all three are feed it to this JOR gate. So x is from here, right? Then we have y. So let's take this as, so we have y, right? And then for z we have this. Okay, now this is your circuit for full adder. I think these concepts are very much clear to you, and still you have any questions, you can write in the message box. Okay, so thank you, thanks for watching.